Welcome to the Knowledge Graph seminar. Today, we are in the week 7 of the course, and we have been talking about how do users interact with the Knowledge Graph. In Tuesday's session, I introduced different interaction paradigms under which users consume the content of a Knowledge Graph. We discussed some visualization principles that we can use for designing a user interface. And I also gave an overview of two specific techniques, structured queries and natural language query answering, which can be used for accessing a knowledge graph. Today, we are fortunate to have with us two experts on each of those two specific techniques. Professor Bob Kowalski, he's a renowned computer scientist and a logician. He has devoted his career to developing computational models of human thinking, for which he has been recognized by an HKI Research Excellence Award. He is also the founder of the whole field of computational law, for which he was recently awarded Stanford's Codex Prize. He will be talking to us about how we can use logical English for accessing knowledge graphs. Michiharu Yasunaga, he is a PhD student at Stanford. He works with Percy Liang, and his PhD thesis and PhD research is on natural language query formulation for knowledge graphs. So we will begin by first Professor Kowalski telling us about logical English. There will be 30 minutes, and then for 30 minutes, we'll hear from Michiharu, and then we'll have 20 minutes discussion towards the end. So Bob, over to you.
Okay, thank you very much. I think I have an option of sharing my screen, and I think this is my screen, and I think we're ready to go. So thank you very much, Vinay, for inviting me to give this little talk, and it's a great pleasure for lots of reasons, one of which is it's an occasion to go back to Stanford in a way, having been a student there some years ago, where I studied logic with people such as Dana Scott and others. So it's a great privilege to be invited to return to Stanford, although remotely in this way. So I'm sharing my screen, I think. So this talk has three parts. I will relate logical English to, well, what I used to know as semantic networks, and hopefully there's enough of a relationship between the semantic networks that I used to know and the knowledge graphs that you're concerned with today for that part of my talk to be still relevant. I will then move on to a particularly interesting technical topic concerned with existential quantifiers, and then finish with a rather challenging example that comes from the domain of law. Well, first of all, logical English, viewed as a computer language, is just syntactic sugar for logic programs. It's very close to logic programs, and it's very easily to translate into logic programs. On the other hand, it's inspired to a large extent by the language of legal documents, and you'll see the last example shows, I'm not sure if you can you see all of this in the corner here? Wait a minute, I think that's better. Wow. So you'll see that the my last example is an example of a legal document translated into logical English. Now, the great virtue and the great selling point of logical English is that it can be read without any training in mathematics, computing, or logic. It may not be that easy to read if you have no knowledge of the topic of the problem domain. For example, in the example of international swaps and derivatives, you may find my example difficult, but it's not because of English and it's not because of logic. It's because the domain of swaps and derivatives is not one that most of us are familiar with. On the other hand, to the extent that logic programs already are relatively general purpose, logical English, which is syntactic sugar for logic programs, might have the potential to be a general purpose computer language for the future. And as such, it has the advantage of being understandable by people who are affected by computer programs, and it allows them to understand what the computer programs are implementing. So I would like to believe that there's a future for logical English, and it might have the potential to render existing computer languages potentially too machine-oriented and less human-oriented than we need for the future. There have been several implementations of logical English, starting with an implementation by Jacinto de Villa, which is online and can be played with to some extent, and then two other implementations by master's degree students at Imperial College, the first of which by Karadatchev looked at international swaps and derivatives, and the second one by Fu looked at a simplified loan agreement. But work is going apace, and we're hoping that before the end of the year, we'll have something online which many more people can play with. Well, what is the background? Other than logic programming, there is related work, of course, in the field of controlled natural languages. And in particular, ACE, Attempted Controlled English by Norbert Fuchs, and PENG, Processable English by Rolf Schwitter, are both along the lines of precursors to some extent to the work I'm presenting here. More recently, there's been a number of developments specifically building on logic programming with a kind of sugared up syntax, but focused not as a general purpose language, but rather as a domain specific language for legal applications. In particular, blocks, the language developed by Jason Morris, is oriented towards what is known as rules as code, which is oriented for use by legal draftsmen who are working with legislation. Whereas lexicon, on the other hand, by Henning Dietrich, is oriented towards smart contracts running on blockchains. Both of these have been developed within the last year or two, and both of them are forms of sugared syntax for logic programming. But the closest work to what I'm presenting today is by Rolf Schwitter on PENG ASP, which is syntactic sugar for the logic programming language answer set programming ASP. And in my opinion, it renders ASP with its conventional syntax totally redundant, because who would want to use a symbolic language when a readable English version of it is readily available. Work on logical English to some extent goes back to 1982, when I published a paper reporting work I had been doing with children, starting with my own children, and teaching logic as a computer language in their local school. We started with semantic networks, which were a nice graphical representation of knowledge, and showed how semantic networks could be extended to include rules. So here, for example, if you have, let's say, two parts of some item, let's say a bicycle, and you have a transitivity relationship between X, Y, and Z, you can conclude that if X is part of Y and Y is part of Z, then X itself is part of Z. And we had both the semantic network representations and the English-like representation that you can see here. So logical English is a kind of further extension of the work that we started with children in 1982. The basic form of logical English is the use of clauses, as in logic programming, which have a single conclusion and multiple conditions joined by and. Conclusions and conditions are themselves atomic formulas or predications, and we write these in infix or prefix or postfix form, and we have declarations to indicate what they look like. So we have, for example, instead of writing X part of parentheses X comma Y parentheses, we write X is part of Y. So it's quite readable, and it requires no training to understand the symbolism involved. So we have predicates which are infix, prefix, or postfix. An interesting feature of logical English is that it exploits the fact that in logic programs, variables quantification is implicit. There's no need to say for all x, for all y. We simply use variables x and y. Now, logical English builds on that by using the indefinite articles a and an to introduce the variable, and it uses the determinate article the to refer to previously introduced variables. And these are followed in turn by a common noun, such as a part or an account. And the common noun part or account gives us the type of the variable. So this to some extent extends logic programming by the introduction of types, because all variables are introduced by determiners, which in turn are followed by common nouns, which give the type of the variable. Moreover, the infix form typically interposes prepositions. So part of, the of is a preposition in this example, and that gives us the role of the predicate. And you'll see examples of other prepositions which indicate other roles. And again, that's a kind of extension of conventional logic programming. So what are some of the distinguishing features of logical English that distinguish it, for example, from other controlled natural languages used in computing? Well, first of all, there are no pronouns such as he, she, or it. ACE, the most well-known controlled natural language, does allow such pronouns, and it does disambiguate them in a particular way. But sometimes the disambiguation is unintuitive and not what a normal person would usually do and would understand when reading such pronouns. And pronouns are a huge, possibly biggest source of ambiguity in ordinary language. Another feature of logical English is that all nouns and verbs are in the singular. There are no plural nouns or verbs, and arguably, I could argue, if there were more time, that the singular is more precise than the plural in most cases. For example, boys like girls is a rather imprecise statement, but if you said a boy likes a girl, maybe you're getting closer to something which is less ambiguous. All verbs are also in the present tense. This is perhaps quite surprising because much of the complexity of learning a language is to learn all the different ways of expressing past, future, pluperfect, what have you. But we avoid these tenses because time is reified, and you'll see what I mean by that in a moment. We simply refer to time, and if the time is in the future, then it allows us in the present tense to talk about a future time. If the time is in the past, then it allows us to talk about the past again using the present tense. But let's relate logical English to the previous lectures that you've seen. So Vinay gave this example of a scenario involving a conflict of interest between a person and a company and a chemical. Looking at from the point of view of logical English, we would represent this graph in an English-like manner by giving predicate declarations at the beginning of, let's call it a program for want of a better terminology. So at the beginning of a logical English program, we will declare our predicates. So for example, we might say that a person is involved in a study, and that represents the bit of the knowledge graph that you see over here. We would similarly say that a study is about a chemical. Again, by using the indefinite articles a person, a study, we are showing what types we have in our language. which can in turn be used for variables or for instances of those variables. A company funds a person. And this shows our preference for the present tense, and where appropriate for the active voice over the past, the active voice over the passive voice, but not necessarily all the time. A company produces a product, and a product contains a chemical. So let's see how the semantic networks that we played with in 1982 might apply to such a knowledge graph represented in logical English. So for example, suppose we have a company produces a product and the product contains a chemical. We might then conclude that the company has an interest in the chemical. And of course, in logical English, we would write it this way. The conclusion first, the company has an interest in a chemical, and I'll explain why an interest is in red in a moment. A company has an interest in a chemical if the company, see the second time I mention company, I use the definite article the. The first time I use the indefinite article and that's a general rule. Whenever a variable is introduced, it's accompanied by the indefinite or an. And when it's mentioned again in the same sentence, it's introduced by the. So a company has an interest in a chemical if the company produces a product and the product contains the chemical. Why is an interest in red? Well, the natural English reading does not have a variable for an interest, and yet it's introduced. It's a word. In fact, it's a type of object introduced by an. What I'll be arguing in the second part of the little lecture today, I'll be arguing that an interest is a hidden existential quantifier. But otherwise, all variables and conditions are universally quantified, and their scope is the sentence in which they occur. And I've already mentioned this. Common nouns represent types, and is used for the first occurrence, and the is used for later occurrences. I seem to be right. Well, we could look at more involved examples, and here's another example, Vinay's second clause, and we can represent that also in a graphical manner. And as he pointed out in his talk, if you want to represent this with binary predicates, you need to introduce, you need to do reification, and here we reify the conflict itself, and then we have binary relationships. And notice that reification I've highlighted in red because it's existential. A person has the conflict of interest over a study with a company, blah, 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 blah. In red, I've got the existentially quantified variables. Let me point out that variables can also be named by symbols. So there's no need to always refer to types of objects simply using English. We can combine English with symbolism as long as the symbolism is one that would be unintelligible to a child of primary school age. Here's a more interesting example because it shows how reification of time allows verbs to be expressed in the present tense. And it also allows the logic to be much simpler than related logics that involve modalities and possible world semantics, which many people find beyond their level of education. So in this example, we see that the conclusion is that the balance in an account is in an amount C at a time T2. If an amount A is transferred into the account from another account at an earlier time, T1, in fact, the earlier time is immediately before T2, and the balance in the account is an amount B at that earlier time T1, and the new amount is the sum A plus B. So that shows to some extent how it is that we're able to restrict ourselves to the present tense by referring to time. I'll use variables for time, but this could be restated without variables. And then I think you'd find that this is not uncommon in the way we speak with one another. I will see you at a time when you're available at the time, we might say in English, even though it might be arguable to some that times really don't exist as things you can see in the real world. Now, the plan is to develop and improve logical English through a series of unambiguous extensions, which can be transformed in turn into the basic form, just very similar to the idea of transformational grammars that were popularized to some extent by Chomsky before he abandoned them. And in one such extended form, we might be able to say something as simple as the balance in an account becomes the sum of A and B when, rather than speak explicitly about time, when an amount A is transferred into the account and the balance in the account is in an amount B. So it's possible to have much more natural expressions, but we're desperate to maintain that the language remains unambiguous. We don't want to introduce ambiguities, partly because it means it's possible to directly execute these by transforming them into basic logic programs. In this extension of logical English, it will be possible to omit roles prefaced by prepositions typically, add extra roles by adding extra prepositions which give other features, and write down these roles in any order. So we might start, for example, with a sentence that says an amount which is 10% of an amount A is transferred into Mary's account from Bob's account on a day if an amount A is transferred into Bob's account from some other account on the previous day. In other words, Bob generously transfers to Mary 10% of anything he has received the previous day. This shows, I think, quite clearly how prepositions serve to indicate roles. So into Mary's account means that she is the recipient of the transfer. From Bob's account indicates that Bob is the donor of the transfer, and amount is the object of the transfer. And that's why I've used the passive voice. So there's nothing religious about using the active as opposed to the passive voice. But here's an indication of how that might be paraphrased. There's no reason why we can't rewrite the same sentence with the same meaning, referring to Bob being the donor and Mary being the recipient, and dropping this irrelevant point that the amount has been transferred into Bob's account from another account. In a language like Prolog, one would need to have an anonymous variable, whereas here the anonymous variable is simply dropped because the role is irrelevant. Well, I see that, as usual, I'm taking up more time than I intended. This is a curiosity I wanted to bring to your attention concerning existentially quantified variables. So if we have an atomic sentence, a fact as it's sometimes called, and it has a variable prefaced by the indefinite article or an, and we, for example, an amount is transferred into Mary's account from Bob's account on the 23rd of November 2020. An amount is not to be understood as all amounts. And this is not universally quantified. We don't mean that every amount is transferred into Mary's account. What we mean is some amount is transferred into Mary's account. What this shows is that if a variable is in an atomic sentence, then it is natural to interpret that variable as being existentially quantified. Existentially quantified with wide scope, meaning that we can refer to that same variable beyond the sentence in which it was introduced. We can, in another sentence, say, for example, that the amount which was transferred is greater than or equal to 10 pounds. This is not true of universally quantified variables. Universally quantified variables are purely local to the sentence in which they are introduced, and they can be reused in other sentences without having any relationship between them. Not true for these existentially quantified variables which occur in atomic sentences. Notice, however, that these variables can be given names, just like we can have symbolic names for universally quantified variables, such as T1 and T2. We can also have names which is effectively the result of what's called Skolemization, introducing either constants or functions for existentially quantified variables. And for example, an amount A0017 is transferred and A0017 is greater than 10 pounds. Now that's true not only of atomic sentences, it's true also of conclusions of clauses which have conditions, provided though for any variables which are not in the conditions. So any variables that are not in the conditions but are in the conclusions are also existentially quantified, and they also have wide scope, which can be reused outside of that sentence. So for example, if I say that an amount is transferred into Mary's account from Bob's account on a day, if the day is the first of the month, then I'm not saying every amount is transferred. I'm saying that some specific amount is transferred. Moreover, that specific amount is a function of the day of the month. And I can refer with wide scope to that amount in other sentences. I can say that the amount which is transferred, no matter what month it is greater than or equal to 10 pounds. So the amount is itself a function of the month. Or to put it differently, there is a universal quantifier here for all months. And it's not that there exists an amount for all months. It's not the same amount for every month. It's rather the other way around for every month. There exists an amount. So this is general. Whenever we have a variable in the conclusion of a sentence, then it is a function, so to speak, of any universally quantified variables in the conditions of the sentence. Well, I think I'll probably manage to just about fit my talk within the time slot. I want to finish by mentioning a very challenging example, interesting if you're so inclined, esoteric in other respects. This work is still being revised, although the latest revision is very close to publication standards. I see I've done a little bit something funny with my. So here's a complicated clause, which is typical of the ISDA International Swaps and Derivatives Association Master Agreement, which concerns early termination of a contract following an event of default by one of the parties. If one of the parties defaults, so that's the first case. If one of the parties defaults, then the other non-defaulting party has the right or the power to designate an early termination date. But there are constrictions and constraints about the time. However, the party does not have the right to do so if the schedule of the agreement specifies that automatic early termination applies. In such a case, the early termination date will happen automatically at this time of the event of default. An event of default arises, for example, when the defaulting party becomes bankrupt or the defaulting party fails to perform some necessary activity. On the other hand, there is a special case to do with a form of bankruptcy, which means that the automatic early termination occurs just before a petition is produced in a court in the relevant legislative authority. Well, obviously I don't want you to try to understand this, but I would like you to notice that this is very much conforms to the strict form of logical English that I've introduced before. Every sentence here has one conclusion and a number of conditions. So we have the first sentence, which talks about the right of a party to designate an early termination date. We have another sentence which says that an early termination date occurs automatically if automatic early termination is specified. So on the other hand, the fact that the first sentence is a rule and the other two sentences are exceptions is dealt with in a manner which is rather standard in logic programming, namely by adding in a negative condition to the first sentence. So the words in the however, the word however is translated into, and it is not the case that automatic early termination is specified as applying. You don't want to understand this in any detail. All you want to see is, first of all, you want to see that it has logical English form, which is basically syntactic sugar for logic programs. It has universally quantified variables with types, with roles, and it also has existentially quantified variables in the conclusion because they do not occur in the conditions. So an early termination date occurs. We're not saying every early termination date occurs. We're saying some specific early termination date occurs, and it is a function. Moreover, it is a function of the event of default and the party who is defaulting, and possibly the transaction. But this applies to all transactions, so I won't dwell upon that. So I think I have taken the necessary amount of time to present logical English in some summary detail. Let me conclude by saying logical English, first of all, is a logic, and it's a logic which is far simpler than many of its competitors, including competitors involving modal logic with possible world semantics, with numerous complications which hopefully many of you will not need to be concerned about. And on top of that, it also has many practical applications. It's also a form of English. It's arguably worth teaching just to teach that English sentences can have meaning. And for them to have meaning, we need to identify their unambiguous intended interpretation. I think many children would be surprised to learn that that is the case. So it is teachable as a form of English. It's also, I think, a potential for computer languages in the future. Computer languages that are not hostage to technical terminology that only well-educated software engineers can understand, but can be understood by stakeholders and can be argued about and explained and debated. So I like to think that there is some future, and the future is bright. So thank you for giving me this opportunity to share my hopes and aspirations with you today.
Thanks.
Thank you.
Yeah, thanks, Bob, for that excellent overview of logical English. We know it is late in your part of the world. If you can stick around for another 50 minutes or so, great. Otherwise, thank you so much for taking the time out and sharing with us your work. We are going to move right along to Michiharu. Michiharu, over to you.
Yeah, sure. Let me share my screen. Oops. Sorry, let me. Do people see my screen?
Yes, we can see your screen.
Okay, sure. Then yeah, let me start. Thank you for inviting me to give a talk. I'm Michi, a PhD student working on natural language processing in the CS department. I'll be talking about our recent work on question answering using pre-trained language models and knowledge graphs. This is a joint work with my collaborators, Hongyu Antoine, and my advisors, Percy and Yuri. Before jumping into the main work, let me first give a brief overview of language models and graph neural networks because they are important building blocks besides knowledge graphs in this talk. The ideal language model is, given a partial sequence of text, we let the model learn to predict the remainder of the text. There are two types of language models. One is autoregressive language model, where you predict the next word given a sequence of preceding words. For example, given the dog chased the, you want to predict the next word such as frisbee. The other type of language model is masked LLM, in which you predict the masked word in a sequence of words. In this example, you want to predict the masked word here, which can be a chase. It turns out that this language model requires various linguistic skills, word knowledge, common sense knowledge, and domain knowledge to do well. For example, in the sentence, Stanford University is located in Mask, California. The model needs to know geographical or factual knowledge. In the sentence, woman walked across the street and looked over Mask's shoulder. We want the model to predict her, and the model needs to know the grammar, such as pronoun. In this case, the model needs to know common sense knowledge, like word associations with fish and turtles. And finally, in this sentence taken from the course description, the model needs to have a world knowledge to predict that the CS520 course is a seminar featuring researchers and industry practitioners. These days, the language models architectures are typically big neural networks, such as transformers, and researchers train the language model on large collection of texts, such as Wikipedia and books, to let the model acquire knowledge. BERT, Rosetta, GPT-3, and so on are prominent examples. The trained language models, or more precisely, the trained representations, can then be adapted to various applications of interest, such as question answering. So how do we usually do this adaptation? Let's say we are given a question and answer candidates. We can concatenate the question and each answer choice to form a sentence, feed it into the language model, and get a probability score of each choice via linear layers. We can fine-tune this model using labeled question answering datasets. The strength of the language models is that they have a broad coverage of knowledge thanks to the extensive pre-training with large corpora, and that they can handle various QA problems, including common-sensical questions like this example, which is not easy to represent as a SPARQL query that can be executed on knowledge graph directly. We will use pre-trained language model as one building block to do question answering later in this talk. Next, let me briefly introduce graph neural networks, GNNs. The basic idea of GNNs is to update the representation or embedding of each node of a graph by letting neighboring nodes to send message vectors to each other. Concurrently, let's say we are at node V, whose current representation is HVK-1. The update rule for each node embedding is to take the representations of the neighbor nodes U and aggregate them to get a total message A, such as taking summation. And then we update the representation of our node V by combining H and A. This combine function could be a linear transformation, for example. This way, we can let the GNN to learn better representations of nodes. We will use graph neural networks to induce representations on knowledge graphs later in this talk. Maybe I'll pause here a bit to see if there are any questions about language models and GNNs.
Yeah, I think it seems pretty clear. And I haven't seen any questions posted to the chat, so I think we can keep moving forward.
Sure, sounds good. question answering is a fundamental problem in natural language processing. And to do well, systems need to access relevant knowledge and reason of it. Typically, knowledge can be encoded in large language models pre-trained on unstructured text, such as BERT, or represented in structured knowledge graphs, such as Freebase and ConceptNet, where entities are represented as nodes and relations between them as edges. Both knowledge sources have complementary strengths. Pre-trained language models have shown great success in many QA tasks, thanks to its broad coverage of knowledge. But at the same time, they may not work well for interpretable or logical reasoning, such as hand-ring negation. On the other hand, KGs are more explicitly represented and suited to structured and interpretable reasoning. But knowledge graphs may lack coverage and be noisy. So in this work, our goal is to leverage both sources of knowledge and do better in question answering. So why is this problem hard and interesting? Let's say the system is given a common sense question, asking, if it is not useful here, a round brush is an example of what? Along with some answer choices like hairbrush and art supplies. We call the set of question and answer choices like this a QA context. Given a QA context, and possibly encoding it with language models, the model needs to first identify informative knowledge portion from the large KG, such as the green box here, and then the model needs to capture the meaning of the question, including a negation in the question, as well as the structure of the knowledge graphs, like the relation between entities, to perform joint reasoning. So these 2 points listed here are interesting research challenges in this problem. In this work, we present QAGNN, a new hybrid model of language model and knowledge graph to solve those challenges. Let me first give an overview of QAGNN. First of all, given a QA context, we will use a language model to encode it into a vector representations, and then use a standard method to retrieve a knowledge graph subset, like linking entities and getting their neighbors on the knowledge graph. Then, QAGNN is based on 2 core ideas. First, in order to better identify which knowledge graph nodes are relevant to the current question, we propose language condition KG node scoring, where we use a pre-trained language model to compute the probability of each KG entity conditioned on the current question. And secondly, to jointly reason with language models and knowledge graphs, we connect the question text and KG to form a joint graph, which we call working graph, and then mutually update their representations via graph neural networks, GNNs. Finally, we combine the representations of the language model and KG to predict the final answer. In what follows, I will introduce these 2 ideas in more detail. Our motivation of proposing KG node scoring is to better identify relevant knowledge from KGs, given a question. Let's say we have this question asking, a revolving door is convenient for 2-directional travel, but also serves as a security measure at what? And answer choices like bank. The real-world knowledge graphs are huge with 1 million entities, and existing methods to extract a KG subset is to identify entity in the QA context like travel, door, security, and bank, which we call topic entities, and then retrieve their 1 or 2 hop neighbors from the knowledge graph. However, this may introduce many entity nodes that are semantically irrelevant to the QA context, especially when the number of topic entities or hops increases. So in this example, 1 hop neighbors may include nodes like holiday, riverbank, human, and place, but they are off topic or too generic to be informative. To address this challenge, we propose to use a pre-trained language model to score the relevance of each KG node conditioned on the question. Specifically, we can calculate the QA context and each entity in the KG and feed it into the language model to compute the probability of each entity. Now, all the nodes in the KG are scored with respect to the question, like in the diagram, where the darker green indicates higher score. For example, entities like robbery and safe have higher relevance score now, and entities like riverbank may have lower scores. The next natural question is how to use this relevance score. One option is to use them to prune KG nodes so that the KG fed into a model can be smaller, which can help to improve the time and space efficiency. Another option is to use the score as an additional feature of KG nodes, which provides a general way to weight information on KG. And we will pursue this direction in our graph neural network architecture we will introduce next. So the next model component is joint reasoning. To design a joint reasoning space for the two sources of knowledge, we explicitly connect them in a common graph structure. We introduce a QA context node, Z, and connect it to each topic entity in the KG. As this joint graph intuitively provides a working memory for reasoning, we call it working graph. Each node in the working graph is associated with one of the four types. Purple is the QA context node, and blue is entity in question, orange is entity in answer choice, and gray is other entities. The initial node representations for the QA context node is the language model encoding, and node representations for other nodes are pre-trained entity embeddings. The working graph essentially unifies the two modalities, text and KG, into one graph. To perform reasoning on the working graph, we design a attention-based graph neural network message passing. The basic idea of GNN is to update the representation of each node by letting neighboring nodes to send message vectors to each other for multiple layers. Concretely, in our model, we update the representation of each node T by this rule here, where M is the message vector from neighbor nodes S. Alpha is the attention weight between the current node T, query vector Q for the source node, and key vector K for the target node. We let the key and query vectors to take the node relevance scores as an argument, and then use the query and key vectors to compute their attention weight using inner product. Okay, so this is a recap of our overall approach, and we have covered the two core ideas proposed here. Now I want to talk about the evaluation of our method. As an experimental setup, we use two popular QA benchmarks that requires reasoning with knowledge. One is Common Sense QA, which has multiple choice questions testing common sense knowledge. Another dataset is OpenBook QA, which has multiple choice questions testing elementary science knowledge. For knowledge graphs, we use ConceptNet, which is an open domain KG with close to 1 million entities. Following prior works in the research field, we link entities in each question to the ConceptNet and extract a subgraph of 2-hop paths to be our input KG. Our KG node scoring idea is performed after this preprocessing. The main systems we compare with are fine-tuned language models like Roberta and previous language model plus KG models such as RelationNet, CagNet, and MHGRN. The main difference between them and our proposed QAGNN is that we estimate the KG node relevance with respect to questions and weight KG information, and that our model mutually updates the language model and KG representations on the joint graph, while prior works combine language model and KG representations only at later stages. For fair comparison, we use the same pre-trained language model, Roberta, for all the systems shown here. Here are the experimental results. We find that QA-GNN achieves an improved performance over previous systems on the two QA benchmarks. To see the effect of the two main ideas we proposed, we also conducted an application study. We find that if we do not form the joint graph of text and KG and mutually update representations, the performance drops about 2%, which is now close to the previous LM plus KG models. We also find that removing the KG relevance score hurts the performance by about 1%. We also find that the KG node scoring tends to help when the number of entities in the question is larger or the size of the retrieved KG is big. On the other hand, the joint graph representation and message passing tend to help when the question has negation. Next, I want to share some case studies of the model. Here, we try to interpret the model reasoning. Given the QA context, we try to trace the attention flow computed by QA-GNN from the QA context node, the purple node, to question entities and to other entities in the KG. In this example, we find that QA context node attends to elevator and basement, and they attend to building, and building attends to office building, which is the answer. This helps us to find a reasoning process from the model. In the second example, we try to trace the attention flow from the QA context node to both question entities and answer entities. In this case, crab on the left and salt water on the right. We were able to find bridging entities on the KG, such as sea and ocean. We also find that QA-GNN can handle some robust reasoning, such as 100 negation and entity substitutions. For example, consider this question. If it is not useful here, a round brush is an example of what? Because the question has a negation, the correct answer is art supply rather than hairbrush. In this original negated question, the model attends to the correct answer, round brush. We then flip this negation in the question on the right. Now the model attends to the entity hair and predicts hairbrush correctly. In this second example, we change the entity in the original question, changing hair to art, and we find that the model adapts the answer accordingly to hairbrush. Here I'm showing more examples of testing such robust reasoning, like changing negation and entity names. And we find that language models like Roberta fails in those tests, but QA-GNN seems to handle some of them correctly. Lastly, I want to share our analysis on when knowledge graph is helpful for question answering and when language model is helpful in contrast. We looked into cases where QA-GNN successfully answers questions, but Roberta language model fails. One tendency is when concrete knowledge, such as facts, antonym, negation provides a key to the answer. In this diagram, we have a question. If you're prone to postpone work, what will you have to do in order to finish on time? The blue nodes here are the question concepts, and red nodes are the answer concepts. In this question, we basically want to find an antonym of the question concept postpone, and the KG provides you an explicit path from postpone to hasten, which is the answer. Another characteristic is when KG paths can provide support for reasoning. In this question, the weasel was becoming a problem. It kept getting into the chicken eggs kept in what? We find that the KG provides multiple paths from the question concept like weasel, chicken, and eggs to the answer concept, barn. On the other hand, we also find examples where the Roberta language model successfully answers questions, but the QA-GNN, the KG-aware method, fails. In such cases, often the question requires subtle language nuance and common sense, and simply relying on knowledge graph paths may lead to a wrong answer or cannot decide. For instance, in this question, James looked up and saw the star twinkling in the black yonder. He marveled at the sheer number of them and the size of what. The correct answer is universe, but the KG-aware method predicts the night sky because it is better connected to the question concepts like twinkle and black on the knowledge graph. But to human eyes, we understand that language nuance kind of makes universe a better choice compared to night sky. Here's another similar example where the question is you would add salt and pepper to what liquid meal if it's bland. And the KG-aware method predicts water probably because they are better connected to the question concepts. But the language model correctly predicts soup, which is a better choice according to our common sense as well. So from those examples, we find that knowledge graph and language model have complementary strengths. So we also conducted an oracle experiment, where if either of the language model or the KG-aware method answers correctly, we count it as success. We find that this oracle can achieve substantially higher performance than Roberta and QAGNN. This result may suggest a potentially interesting future research direction, such as learning to figure out which sources of knowledge, language model or KG, to rely on. Finally, I want to summarize the takeaways of this talk. Our motivation was to combine two sources of knowledge, pre-trained language model and KG, to do better in question answering. To solve this problem, we introduced a new model, QAGNN, which has two innovations. We use language models to score the node relevance condition on the question. This is a general framework to weight information on the KG, like soft retrieval or pruning. We then propose joint reasoning with language model and KG, where we connect the text and knowledge graph to form a joint graph and mutually update their representations. We also found interesting insights. KG node scoring tends to help when retrieved KG is big or noisy, and joint language model or KG message passing tends to help when the question requires rich reasoning, such as negation. Through case studies, we also found that language model and KG have complementary strengths. Thanks for your attention, and I'm happy to take any questions.
Yeah, that's all I have.
All right. Thank you very much. Thanks, Michi.
Thanks.
All right. So we are now in our question answering. We have about 20 minutes.
There are two questions for Bob. The first question is logical English used to write contracts? Does logical English identify flaws in existing contracts?
Okay, that's a very interesting question, because when we looked at the international swaps and derivatives contracts, where the English is very complicated, we discovered, I would say that the English, from my point of view, is very poor. Compared with the kind of English that you find in legislative language. So legislators are typically at the top of the class of legal professionals. Obviously, lawyers who draft contracts are also highly educated, but their command of language is not so adequate, I would say. In any case, with the contracts that we looked at, we found a lot of flaws. In fact, mostly the English was designed to be intelligible to lawyers and not intelligible to clients. I think there was almost a conscious effort to make the English difficult to understand, so that it would produce employment for the legal professionals. Actual mistakes, there are fewer mistakes than you might actually anticipate, but in general, I think, well, let's put it differently. In the field of legislation, there is a large movement towards plain language and clear language. In the field of contract law, there is almost an opposite movement to use obscure language, which requires interpretation. And we discovered many cases where the contract stated something different from what the common law interpretations were, in which case the common law interpretation took precedence over what was actually written down. So yes, there was quite a lot of discrepancy between what was intended and what was actually written.
Thank you. There's another question for Bob. Thanks for presenting the legal knowledge often involves complex temporal constraints involving words like while, until. Any plans of including those anytime in the near future, or any thoughts on how one might go about modeling those?
Yeah, so I think I did give example of immediately before and why and when. So when means X, when Y means X is at a time, if Y is at that same time. So yes, we do and have been working on purely natural language representations of time along the lines that you find in modal logic. But in fact, modal logic, with its use of until and while and whatnot, has very complex semantics. And secondly, there are times when we want to talk about time abstractly, and when we want to talk about time more concretely. So we don't always want to have oversimplifications when talking about time. But indeed, one of the big challenges in the work is to try to make talking about time as simple as possible, but at the same time, not oversimplifying it. Thank you. That's a good question.
Thank you. And there's one question for Michihiro. Michihiro, asking you to compare your QA-GNN with GPT-3.
Right, that's a very good question. So at the time when we worked on this project, we didn't have access to GPT-3. GPT-3 requires you need a permission to use it. And at that time we didn't have, so we didn't really run it. But I think that's a very interesting experiment to do, whichever you want to do. And one thing to note is that GPT-3 is a kind of few-shot learning paradigm where GPT-3 can get, for example, 2,000 tokens in its context, and you feed in some couple with QA examples as a kind of prompting text in the beginning, and then you let the GPT-3 to predict the next words, next sentences as your answer. So I guess in the natural paradigm of GPT-3, we will probably use those few-shot setting, and then compare with our QA-GNN. But the QA-GNN is trained using the all label data available for the benchmarks. So there's some discrepancy here. But thanks for asking this. I think that's a very interesting direction to explore.
Thank you. So Vinay, there is a question I think you might be really excited about in the logical English space about humanity, etc. Do you want to ask that?
Well, actually, I got an answer, very good answer to this question at Mike's class yesterday, and I feel like I can answer that question. But so the question is, sometimes the ambiguity is desirable in a legal contract, and if you use logical English, it makes the contract very inhumane and inflexible. And the answer which I got at yesterday's lecture was that, well, anytime we need to introduce flexibility in our contract, we can explicitly program it. So we can have, so let's say, there's a place where a human needs to exercise discretion, and we could have a predicate whose value is input by a human, right? So you can still make your contract precise, and within that precision, you can provide room for flexibility wherever it is necessary, but you're doing it consciously. You're not just, making it so opaque that you're not clear whether it is intentionally ambiguous versus it is ambiguous by design, right? So I don't know about what would you do? You have a different perspective on this, or?
Well, I certainly agree with everything you've said. So I certainly agree with that. But this is I'm amazed that this confusion still exists. There's a distinction which people fail to make between ambiguity and vagueness. So, and even I've talked to legal, I've talked to legal. What can I call them? To lawyers, shall we say? And they do not make the essential distinction between ambiguity and open texture or vagueness. So there are certain words like being of good character or taking reasonable efforts, which are by definition almost undefinable. And they're essential in law, they're essential in life. On the other hand, ambiguity is something quite different, at least when the terminology is used precisely. There's a difference between ambiguity and open texture or vagueness. So what logical English does is it completely embraces open texture and vagueness. There's absolutely no reason not to have open textured concepts such as being of good character or making reasonable efforts. But on the other hand, we want to avoid saying she doesn't like her anymore. Things of this nature where we have absolutely no idea whether she is Mary or Alice and her is Mary or Alice or somebody totally different. So if you look at it from a purely syntactic point of view, ambiguity has to do with different syntactic parsers. And if you go beyond that, even a syntactic parse can have different semantic interpretations, but they're distinct typically. Anyway, what I would like to urge is greater education to distinguish between ambiguity, vagueness, and open texture. It just seems to be clouding the understanding of this whole field. It's shocking, I would say. Such a fundamental distinction is not made, and ought to be made every day. The Supreme Court, for example, you talk about the Supreme Court in the United States. The Supreme Court does not disambiguate. The Supreme Court adjudicates on how to interpret vague concepts, open textured concepts as time changes. And there are two different schools of thought. Do you interpret a vague concept in terms of what was originally understood in the 18th or 17th century, or do you interpret it as it is to be understood today? I mean, it has nothing to do with ambiguity and everything to do with open texture. Okay, that's a rant, and I apologize.
That's fine.
I saw Michael shaking his head. I'd like Michael to, please, could you give your opinion on this?
Ditto.
You could say more than that. Come on.
I completely agree. I think you've captured it exactly as did Vinay. And that's one of the features, one of the good things you should take away from this particular question and incident is it occurred in class where we were trying to make sure that students do make this distinction, where we tease it apart for them, and where we dispel misconceptions that in order to say something in logic, you must disambiguate everything entirely. That is not at all the case. Logic, the beauty of logic, it allows one to express incomplete information. It gives you disjunction, it gives you existentials, just so that you can capture exactly what you mean as precisely or as ambiguously as you like, without incurring unintentional ambiguity. And so forth. So yes, I'm totally with you on it. It's a refrain that I need to unfortunately speak again and again because of common misconceptions, due to the fact that not everybody learns logic because nobody teaches logic anymore. Another rant which I could get onto for a long period of time. Yeah.
Well, let me interrupt. I learned logic. I learned logic not in my mathematical logic courses, not in any philosophy. I learned logic at the University of Chicago in an English course. I got a D in English. It was because I used pronouns that had no references because I thought I should be a poet. You know, it was not for me to determine what I meant. It was for the interpreter. You know, I was writing poetry. I wasn't writing things that had any meaning. It was me. It was the challenge was for the reader to discover.
Oh my gosh. Okay.
So I think in the context of our class, we are interested in posing questions to the knowledge graph, and there is the approach of posing the questions in some kind of logical English versus using language models or sort of more flexible natural language approach. And you know, the way sort of we frame the problem is that, well, you know, if you use structured English, you have to kind of work on your specification. You have to work on your grammar, right? Which will define what family of queries you're going to accept. And if you're going to use language model, then you're passing some of that burden to the statistics you're going to get from the text, right? You're not going to do all of that yourself by hand engineering your specification. And I mean, I think the question really is that as we go about designing query interfaces for knowledge graphs, how should we actually think about these two different methods? I mean, is one always better than the other? Are they mutually exclusive? Should they be used in combination? So what are your thoughts on that, Bob?
Right. Well, logical English isn't designed to be a query language. Logical English is designed to be a programming language which readers can understand. So at the moment we have a crisis in computing with you know, thousands of computer languages, each with its own syntax, each with its own computer-oriented operational semantics to do with manipulating memory locations in a computer. You know, for a person who, you know, is an ordinary human being and not a computer specialist, these programs are totally unintelligible. So the plan is to have a single uniform way of representing all kinds of computer programs to make them readable. It'll still be difficult, and this is maybe the main point to do with your question, still be difficult to write. In the same way it's difficult to write good, clear English in the first place. So as a query language, it's not going to be all that easy to write strict logical English sentences. So I have no problem with writing ordinary English and then disambiguating it by returning, you know, precise logical English potential interpretations of what a user is trying to actually query. Yeah, so there's a big difference between reading and writing. You know, Shakespeare can be read, but not many of us can write like Shakespeare.
I just don't want to let that go entirely. I think logical English logic is a great query language. If I wanted to find precisely what information I want out of my knowledge graph or database, then it's great for me to be able to define the result set that I want by having a good language that's clear and crisp and unambiguous, and I can rely on to give me those answers. So in fact, it's a fantastic query language. That said, the purpose is not as a query language, it is as a language of capturing definitions and knowledge, and including that to augment what's in the knowledge graph, to give definitions, to give meaning to the concepts in the knowledge graph. That's absolutely what it's all about. But I don't want to say it's not a good query language. It's a great query language.
Michi, do you want to take your perspective here?
Yeah, so I think I can provide more perspective from the kind of question answering aspect. And I think in terms of that, definitely combining, you know, language model and knowledge graph is a good future to go. As I think I show some experience, like Oracle experiments where we do the ensemble of language model knowledge and knowledge graph, and that achieves, you know, much better performance than just using, you know, only one of them, right? So I think that's a good way to go. And I think the work I presented today is kind of, you know, first attempt to kind of combine knowledge graph and language model as like a joint graph and let the model just learn from data to do interaction between them. I think that's a kind of very kind of preliminary way to go. And in the future, we might want to design more kind of modular way for interacting between language model and knowledge graph. So for example, language model can kind of mainly focus on like a language, more like a language knowledge, and knowledge graph can focus on like a factual knowledge and so on. And then the model can kind of, do kind of given a question, there's a kind of some meta level module that kind of decide which one to rely on and so on. I think that kind of more crisp and modular architecture design will be an interesting future research to do. Yeah, that's the perspective I have right now.
Okay. Yeah, I mean, I think to sort of synthesize from there, I think in the previous lecture, I tried to make the argument that we shouldn't get hung up on using just one method for accessing the knowledge graph. I don't think the question really should be that is logical English the way to go versus are the language models the way to go. I mean, I think we can use a combination of techniques, and sort of one design template I had argued in favor of was that, well, when you are accessing the knowledge graph, maybe you want to start with some kind of giving an overview of the information in the graph, and then maybe the user can perform some searches. They can further narrow down what they're looking for, and then maybe they can pose a more precise query, which really which gives them exactly what they're looking for. So I mean, it is possible to come up with combinations of these methods, trying to sort of best fit what user is trying to get at, right? And I don't think it necessarily has to be one versus the other. Yeah. Mike is not happy with that answer.
No, I'm not happy with knowledge graphs. That's my problem. Knowledge graph is a semantic net. The links don't mean anything. They are just strings of characters attached to arcs. Until you tell me what they mean, it doesn't mean a damn thing to me. And what logic does is allows you to give meaning to those relationships and to relate those to other things. I'm happy writing them in Prolog. I'm happy writing them in logical English, but as long as they are written down so I understand what they mean, that's what I care about. And so just a graph without giving me anything but a bunch of strings of characters attached to arcs and nodes is not going to be very meaningful. I don't know what it means. Where's the documentation? The documentation should be in the system as well. It needs to understand the knowledge, not just the data that's sitting there in those links. And that's what logic brings to the table. And I think we've not been adequately talking about that aspect of it, although to your credit, Vinay, I think you have spent some time in multiple lectures talking about how one would define the meanings of those relationships.
Right.
Anyway, that's why I was shaking my head.
Yeah, so I mean, again, I think it's the perspective you've taken here is that there is a spectrum, right? And there is this idea that, I mean, there is an expensive way to get to the meaning, and then there are sort of approximate and cheap ways to get at the meaning, and I think we want to allow for all possibilities, right? So
I just like to have the machines have more intelligence in them rather than relying on the human beings who use the machines to have to supplement them, providing nothing but a bunch of data which is uninterpretable. So
yeah, I mean, I think that is a search model, right? So search and information retrieval largely relies on that, and it seems like a killer app. It's incredibly useful to people.
I'm not disagreeing it's useful. It doesn't make me happy because I usually have a requirement, as we've had a discussion in the past. I'm looking for reliable data, which is easy for me to specify, where I know precisely what's being said. I don't want guesses, for one. I don't want to have to fill in and say, what's the next word, without knowing what the words previous to it actually mean, which I think is partly what our previous speaker was actually saying we need to have as well. So I want to know what the meaning of those concepts are and then to utilize that. I'm more interested in the knowledge, the definitions of those relationships than I am in the data that those relationships are capturing. Right. We often talk about not big data, but small data. What I would really like is a system that has so much knowledge that you can squeeze every little bit of conclusions out of a small amount of data. That to me is intelligence. And I want to see more of that in our systems. and more of that knowledge built in there, which allows us to squeeze a lot out of a very little amount of data, rather than squeezing a little out of a lot of data.
Yeah, I mean, I think that there's, as I said, there's a spectrum of applications, right? So
I'm not disagreeing with that, but you were asking me why I'm representing the other side of that spectrum,
Sure.
the other end of that spectrum, and making sure we haven't forgotten that end of the spectrum.
Absolutely. Yeah, so I think we are at the end of the class time. So I'd really like to thank Professor Kowalski and Michiharo, and Bob, especially, you stayed up late. It's like 2:00 at night. It's amazing, your dedication to the topic, right? So thank you very much. And thank you, Michi, for taking the time off to come talk to our class. Really enjoyed your presentation. With this, I'll conclude today's session, and our class will continue next week. And next week, we are going to be focusing on how to evolve a knowledge graph. Thank you all, and bye for now.